Okay, then let's move on. For everyone who joined recently, a quick reminder, please feel free to drop questions in the chat during the session. My name is Yasmin and we are currently at the second talk for this session at ISS. Now we will hear more about lines and tactile line tracing. And this will be brought to us by Jiakun Yu. Jiakun, are you here?
Hi there, my name is Jiakun. I'm the second year PhD student in the University of Sydney, and today I will be presenting our paper, Composite Line Designs and Accuracy Measures for Tactile Line Tracing on Touch Surfaces. This work was done in collaboration by HCI labs between the University of Sydney and Monash University. To begin, looking at these three pictures, maps, a light rail transit map, and a plot of two foreign exchange rates. What would it be? What is common between all of them? Well, it's lines. Tracing lines is something that we all can do visually, but what would it be like if we couldn't utilize our sense of sight to do these tasks? By using the technology, you can still grab some information from those graphs, but eyes-free. Research about eyes-free operation of devices, including using tactile feedback and auditory feedback, and so on. And sometimes they're a combination. In our study, we proposed a method to evaluate the tactile feedback and different vibration algorithm for tactile line tracing. This is an example of the user study setup. Of course, it is important to decide the content to be tested. Some researchers have looked into shapes tracing by using simple shapes such as triangle, square, circle, and pentagons. In the beginning of our research, we also looked into shape tracing. This animation is one of the pilot study results for the shape tracing. We found that user would eventually start guessing the shape. As you can see, there are a lot of straight, uninterrupted line tracing. But we found that they cannot guess lines. Especially, there are many applications like digital maps or data plot where information is not encoded in shapes, but lines themselves. So we are more intended to process eyes-free line tracing using tactile feedback methods. When it goes to line design for the user study, what should be considered in the line designs? There are some unique challenge and important factors involved in tactile line tracing, including different angles and curved segments. But we found that study often underexplored for those different features. For instance, curved segments, a feature seen in many line-based maps and plots, were notably missing in recent studies. In addressing this problem, we include many different composite lines that can be formed to create acute, right, and obtuse angles. We want to combine features together, but the line you see on the bottom seems too hard for some users. Some would spend over 5 minutes tracing some lines. To reduce the length of our user study, we decide to redraw the lines. As a result, we developed this new composite line set that also can be used for the further line tracing research. And they are used in our first user study. We proposed two different methods of eyes-free line tracing, non-directional and directional feedback. Non-directional feedback is a feedback that provides only contextual information about an individual position on the line. An example of this is by varying the intensity of tactile line tracing feedback as a user deviates further away from the line. And the directional feedback, on the other hand, are methods which try to direct the user in a certain direction if the shape of the line to return to the line. An example of this can be seen on the screen now. You can check our paper for further information that how both feedback have been implemented. One more big challenge in line tracing is accuracy metrics. How can we measure the accuracy? One of the measures that commonly used to compare the participant is the time or speed. While in our user study, some section of the line can be skipped in tracing, as the picture shows, leading to the shorter time. Researchers have used other creative to overcome these issues. Cagatay asked participants to redraw the traced line immediately after tracing, and the DMTS was used by Chau that asked user to trace 2 lines instead of 1 and compare if they are the same or not. Both methods are very creative, but it's a bit time-consuming in our user study. We introduced 3 accuracy measures: length error, area error, and Fréchet distance. They are all computable without further user involvement, which is better for the future research. But I want to state more on Fréchet distance. Intuitively, the Fréchet distance between 2 curves is the minimum length of the leash required to connect a dog and its owner as they work without backtracing along their respective curve from one end to another. Not considering their tracking speed is one of its advantages. These alternative methods have not been explored in the other line tracing study nor in the HCI context. So we had 2 user studies conducted to evaluate our tactile feedback methods. The first user study, we had 13 participants. Participants were blindfolded and asked to place on a noise canceling headphone. Then for each of the methods, we provided user an initial learning period on how to utilize the method. Then they were asked to trace randomly selected unseen lines from the set of lines with the feedback and redraw the line from the memory 5 times. After tracing 5 different lines, they were asked to fill in the NASA task load index survey to judge how intense each method was. So here is a section like a poor line traces. As you can see, many people utilize a star or campus bearing technique when they got lost. And here are the result of the redraw from those lines. Here is a section of good line tracing. And here was the resulting redraw from those lines. Our second user study was a follow-up study to the first user study. So we want to find out on which of the 4 measures best determine users' line redraw accuracy. So we asked 90 participants to rate 153 line redraw pairs on an online questionnaire, resulting in 4,590 line rating in total. As seen in this image, users were asked to select if they will redraw the line on the right was either very similar to very different. So let's look at the result of the tactile line tracing user study. Figure A showed that participants were made more errors at lines section than at joints. Figure B shows that different joint types are harder to trace with different feedback types. For instance, line only result in having the best performance for right angle joints, while the virtual force worked best for acute angles. Similarly, figure C shows different line types also perform differently. Notably, horizontal and curved lines were much easier to navigate than the vertical and diagonal lines. These indicate that different types of line segment are necessary to be included in the line tracing study to acquire versatile results. Which means like segmented line design is much more important. To examine the discriminative property of each measures, we compare the Likert rating of the best and worst traces with respect to each measures. This figure reveals that all the measures show the significant change of the redraw quality rating between high and low groups. However, out of the 4 measures, Fréchet distance show the highest difference between all of the difference. To further examine the correlation between each of them, we did a Pearson ranked order correlation. The result of the redraw similarity evaluation showed that high correlation between TLE and TAE, but low correlation between T and FD. This is indicative that Fréchet distance could produce independent information to the commonly used time metric. More importantly, Fréchet distance show moderate correlation with user rating of the redraw FD survey and comparing to T survey and LE survey. This finding is indicative that FD is moderated correlated with user rating of redraws. As you can see in this picture, quality of the redraw is much more related to the Fréchet distance. So finally, to summarize this paper, I would like to highlight 3 main points. In this paper, we used a segmented line design with different geometric feature that is suitable for vibrotactile line tracing and evaluate different accuracy metrics. We introduced the applicability of different accuracy metrics that can be applied to the tactile line tracing task on touchscreen. Especially, we provide an additional new measures for further study and system to judge the accuracy of tactile line tracing, Fréchet distance, since it is a better indicator out of the 4 accuracy metric for maximizing the recognition of the lines. Overall, the contribution of this paper should inform future study in tactile information tracing. This project was funded by the Australian Research Council. We would also like to thank the participant of all our user study and the member of the 8th lab for their support. And thank you for your listening. That's all for this presentation. Thank you.
Thank you, Jiakun. We lost you for a brief moment there. So if there are any questions and you said this in your talk, don't be mad at the person asking the question. It was just a short time when you presented the results. But thank you for the interesting presentation. Let's see if we have any questions already. Yeah, we have a question.
Hi, I saw that you used like a crowdsourcing approach to compare the similarity of the lines. So just out of curiosity, why did you not use some kind of an algorithmic or computational approach to calculate the similarity between the designs?
So the things like we use this Fréchet distance algorithm just for this algorithm to compare the redraw and the redraw and the original lines, and they have their line pairs that can do the computational 1 by 1 in this algorithm. I'm not sure what you mean. Are you mean by like machine learning algorithm or something like other mechanism?
So maybe I just got it wrong in the presentation, sorry, but I thought that you would use users to check if the reproduction of the line is similar to what the actual task was. But maybe I just got that wrong. So
yeah, we just so we did the algorithm by ourselves, but not the user. The user will just do the one user study, and so they do not need further involvement. So this is very suitable for users. Yeah.
Thank you. So let's see, do we have any questions in the chat so far? There is another question.
Hi. I was wondering who the intended users are. Is it people on the road who doesn't have time
Yeah,
to
yeah.
or is it blind people?
Yeah, that's what I mean. So we intended to put this application to the visual impaired people, or sometimes if you just have like eyes surgery, but you just hurry to know some information from some graphs, or it's mostly designed for the visual impaired people, but we avoid to use these terms in our presentation because maybe we think maybe cause some trouble, but it intended to design for them. But if there for sometimes that you cannot use your eyes, I mean, for some situation, you can still using our product application. Yeah.
Okay, thank you for your answer. That makes sense. But if you say that you sometimes may use it temporarily because you just got eye surgery, then I'm wondering about the question of how long do you think it will take people to learn to use it? I mean, if you're blind permanently, you have time to learn, I guess. But if you have to use it temporarily because you got eye surgery, you have to be able to learn quickly.
Yes,
So how
that's a good question. In our user study and pilot study, we gave them 5 minutes to learn our all devices. And for the result, it shows like they learn it quite quickly, and it's quite easy to suit them because it's just vibration. And for different algorithm, vibration technique, vibration method, when they got the different location, if they are not on exact line, so they will vibrate different. So they can learn it very quickly, probably 5 minutes, yeah, I think.
Hey, Jiakun, thank you so much.
Yeah.